All right, so now we're going to talk about one of the greatest comparison-based sorting algorithms, and that is quicksort. So again, let's just try to get the basic inspiration if you were to just think from first principles. So you want to sort a list of size n. Okay. So again, the base case for this would be just like in the case of the merge sort algorithm we saw. If you have just one element, then the sorted entry is going to be just a single element. And the inductive step that we can think of, another strategy, is we somehow select one. So if you have a list given, just choose something, okay, one of the entries within the list. So we can call x equal to select one of the elements. And then after selecting, now you can think of, with respect to this particular value of x, so this is our x, we can reorganize the elements which are on this side to be less than so this can be less than x, and on this side it can be greater than x. So can we split the list in that way? So once we have done that all the entries are less than x at this side, then it's just a matter of sorting each of these, whatever is there on the left hand side recursively, sorting whatever is there on the right hand side, and just applying a concatenate operation. So you can think of L1 is derived by splitting, let's say, greater than equal to list with respect to x. And then another list we can create by splitting with respect to less than x. So this is greater than equal to x. So L comma x. And then L1 dash is going to be so L1 dash will be obtained by sorting this L1, and L2 dash can be obtained by sorting. So this is the recursive step, as you can see, L2. Then the overall sorted list is just going to be a concatenation. So it's going to be a concatenation. So because we have considered greater than equal to, so suppose we are sorting this in the descending order, then it's going to be L1 dash comma L2 dash. Now, of course, we can write down this as less than equal to and greater than, and then we can make it an increasing order as well, but just to kind of show that it doesn't matter which order you want to do, but you can apply in this way. So in this case, it just happens to be just a concatenation operation, which is a very trivial sort of operation, unlike the merge operation. So this is our decomposition step, and this is our recomposition step, which is just involving concatenation in this case. So I hope like you can see the overall strategy in this way. And now the question is that how are we going to execute such a strategy? So let's just first discuss a few things. So the selection of an arbitrary value that we did, this x, is what is referred to as pivot in the quicksort. So this overall strategy that we are presenting here is the quicksort strategy. So this is also a recursive divide and conquer algorithm. Okay. So unlike the merge sort, you can see that the merging is trivial, which is essentially a concat operation. And this quicksort essentially turns out to be the fastest comparison based sorting for arrays. Okay. Why is it considered to be the fastest? So first of all, we will soon see that the worst case execution time for this is n square. And yet the quicksort, if implemented cleverly, I'm really apologizing for my really poor handwriting. Somehow the pen is not working exactly how it used to work. Okay, so if implemented cleverly, virtually always runs in order of n log n in practice. And not only that, it is running an n log n in practice, plus with a smaller constant factor. And that's what positions the quicksort in the fastest category. Now, it's not that you have to take my word for it, but you're going to prove it. And that's going to be your next homework, to actually show how quicksort is the fastest algorithm. Because it's one thing to just talk about it, but another thing is to actually show it. So let's take just an example to first understand, because we need to understand this algorithm thoroughly. It's a beautiful algorithm. So 4715930. Let's say I pick some random numbers here in an array. Okay. So now the first step for performing the quicksort, we saw that we have to select an arbitrary value, right? Or arbitrary number out of this list. So let's say your strategy is that I'm always going to pick the suppose this is our A. I'm going to always pick the first element. That's your strategy for selecting the pivot. So based on that, your pivot is here. So your pivot is essentially 4. So then you have to now reorganize the values which are less than 4 on the left hand side, and that is greater than 4 on the right hand side. So what are the values that is less than 4? You have 1. Then you have 3 and you have 0. And what are the values that is greater than 4? You have got 5. No, first is actually 7. First is 7, then you have 5, and then you have 9. So again, the strategy is to select. So this is our pivot here at this step. So again, at this stage, again, you divide. So here we divide it into 3 pieces. So here your pivot is going to be the first element again. So this is going to be 1 as the pivot. So what goes on the left is what is less than the pivot, which is 0. What goes on the right is going to be 3 because that is greater than the pivot. And then likewise here, the first entry is our pivot. So it's going to be 7. We select this as the pivot here. So what is less than 7 is you have 5. And then what is greater than 7 is 9. Okay. And then as you can see, we are simply concatenating. So this comes down, which is 4. And you can see that just by concatenation, you have got the sorted list. So now let's now see, now just similar to the merge sort, one can draw out that, okay, oh, this is going to be log n. And this is going to be overall n, so therefore it's n log n algorithm, right? Okay. So now let's see if suppose this is the input that you provided to this quick sort for sorting, which is essentially 0, 1, 3, 4, 5, 7, 9. Suppose this was your input to the sorted to the quick sort algorithm. Okay, and your strategy for pivot selection is still the same, which is just the first element selection. Okay, so what are you going to select as a pivot here? Okay, you're going to select 0 as the pivot, right? Great. If it is 0, there is nothing that is less than 0, so it remains empty. And the rest goes here, which is essentially 1, 3, 4, 5, 7, and 9. So again, here you select your first entry, which is 1 as the pivot. And there is nothing that can be put here. And the rest goes here. So you see where it is going. So if you have provided a sorted list as your input, and your pivot selection strategy is always selecting the first element, you can see that this whole series of steps would be order of n, right? So then, therefore, in such a case, if this one is n, the total number of entries, so this would end up in order of n square. So what did we understand from here? When the input is already sorted, choosing the first item as pivot is, we could call it disastrous. So one may say, oh, I'm not going to just choose the first element as the pivot. How about choosing the middle one as pivot? Now, if you choose the middle one as pivot, if you come up with a palindrome sort of sequence, then in that case, you will hit the same situation. In other words, if you choose a pivot selection strategy which somehow follows a particular pattern, you can always come up with another pattern to beat that pivot selection. Therefore, the cleverness of the quicksort algorithm is actually dependent on the choice of the pivot. So I'm just going to here give you two main well-known strategies for choosing pivot. So one is just random selection. So you just flip your coin and just select a pivot. That still at least will provide a better distribution than choosing a pivot which follows a particular pattern. Another well-known strategy is called a median of 3 strategy. So median of 3 strategy in the sense that you take the first, last, and mid, and you take the median of these 3, and that is your pivot. This is a very, very common strategy that is used in the pivot selection, because sometimes randomization can lead to sort of, you can say, unstable number of steps when you run multiple number of times. But if you take the median of 3, at least it has got a more consistent sort of series of steps. Okay, so now I'm going to talk about how we can actually make this quicksort algorithm in place sorting algorithm. So now let's see how we can actually make the quicksort somehow or other be an in-place strategy. And remember, in place means we are not incurring any other overhead. We are, just like we saw in the merge sort, there was an overhead of using that array B as an auxiliary storage when we were merging. So how can we achieve the sorting without paying any extra memory overhead? Okay, so please follow carefully. Suppose my elements are, let's say, 3, 4, 0, 9, 8, 7. Sorry, just follow 9, then 5, 7, 4. Okay. So our starting position is I and ending position is J, as before. So remember, we need to somehow follow this whole pivot selection and then the recursive strategy of reorganizing the elements in such a way that on the left side of the pivot, all the elements which are less than the pivot comes in, and whatever is on the right side of the pivot, they are greater than the pivot. And we have to go through this organization without incurring an additional storage. So that's our goal now. Okay. So first thing, what we are going to do is that we are going to assign a new index, let's say M, which is the one that is just before the I, right? So this is going to be essentially I minus 1. Okay. And we are going to take the jth place and call it N. So N points here, and M points just the position before I. Okay. And what we're going to do is that first step is that we swap. So suppose our pivot happens to be this one. So this is suppose our pivot. by following some strategy, some random strategy, we arrived at this being our pivot. So what we do is that we're going to swap the, so suppose this is our array A. So we're going to swap A of n and the pivot. Okay. Let's call it A of j, because at this point, let's say we have the I position and we have the j position. Okay. So the first step that we are doing is that we're going to swap. We are going to bring the jth entry to the position of the pivot and send the pivot out of this range. So after we do that, what do we get? We essentially get 3, 4, 0, 9. This is going to become 4, then 7, and this is our 5. Okay, so this is our pivot which has got shifted to the jth position, right? So this is the jth position. And we are also having n assigned to j. And we have m assigned to the position before I. Okay. So now the goal is to work on whatever is in this range between what is sandwiched between m and n. That's what we're going to work with. And we have positioned the pivot in this last jth place. Okay, so what I'm going to do now at this point, we are going to we're going to advance this m. Okay, we're going to advance m to the right, and we're going to advance n. We're going to advance n to the left. So how much are we going to advance? We're going to advance m to key that is greater than equal to pivot. Okay. So what we want to achieve here? So we want to achieve, so what is the goal? That we want all, so first let's write down. So here we have got m equal to I minus 1 and n equal to j. So all items that are left of m have a key that is less than equal to our pivot. Let's call this P. So all the items that is left of m have a key that is less than equal to pivot, and all the items that are to the right of n have a key that is greater than p. This is what we want to achieve, okay, by moving these two pointers. So this is our goal for the movement. Okay, so what do? We advance m to key that is greater than equal to pivot. Okay, and we decrement n to key that is less than equal to pivot, right? So we keep moving forward until we find a key that is greater than equal to the pivot. Okay, and at that point what we do is that we make a swap. We swap a of m and a of n. Okay, Let's see this in action so that you are clear in terms of what is going on here. Okay. So we are advancing M. Okay. So we are going to check against 5, right? So is 3 less than 5? That's great, because we have to reach a key that is greater than 5. So 3 is not greater than 5. So we keep moving forward. 4 is not greater than 5. 0 is still not greater than 5. Then you reach 9. 9 is indeed greater than 5, right? So you keep going forward. So 3, 4, 0, 9, 4, 7. And here you have 5. So we are looking in this range. This is your M. This is your N. So after advancing M, it stopped here because it reached a key which is 9, which is greater than the pivot. So this is our pivot. And then likewise, N kept decrementing. Oh, I think this is 8, sorry. Made a mistake here. Just to be clear, so this is 3, 8, 0. Okay, the entries were 3809574. Just to, if you're taking notes. Because I don't want to have you stumble upon this. Okay, so I hope you noted this correction. So the entries were 3809574. Okay. So let me just
Wait, also, you said you were decrementing N, but like you only like while the M advanced value was less than the pivot, you weren't decrementing N though, right?
we are going to decrement N. First, we are advancing M, and then we're going to show what happens when you decrement N. Let me just first show. Let me just correct this first. Okay. So I somehow showed the configuration after we have swapped. So I just want to go step by step. So this is 3809475. Okay. So we're going to get this M incremented until the point we come to a key which is greater than the pivot. Okay, let's make sure we understand this. So we come to a point. So 3 is less than 5, no problem. Then we came to 8. So 8 is a key, okay, where M is going to stop because it has reached a place where it is greater than the pivot. Okay. And likewise, N is now decrementing. So 7 is greater than 5, which is fine because it has to reach a point where it is less than 5. So it is going to stop here. So N is going to stop here upon decrementing. Any question on this? Okay. So now I can copy paste this. Okay. So at this point, we are going to, so we're going to swap. Okay, so we're going to swap. So after swapping, you bring 4 here and 8 here. And your M is still pointing here and N is pointing here. Okay. So notice what we have done by doing this. What we have achieved is that we are progressively moving forward. So in this range, right, we have achieved what is less than 5. And in this range, we have achieved what is, so this is greater than 5. This is less than 5. That's what we have achieved so far. Okay. So we're going to keep moving forward. So again, move M and N. So M moving in this direction and moving in this direction. Let's see. Okay. So right now, what we have got, so you have your 4 here and 8 here. Okay. And M is pointing here at this moment and N is pointing here, right? So now we're going to continue. So now because of the swapping, so now the 4 is now less than 5. Okay, keep moving forward. 0 is less than 5. Keep moving forward till it reaches now the new place where M is going to stop is here. Okay. And likewise, N is starting from here, which is 8. So 8 is greater than 5, which is fine. 9 is greater than 5. Keep moving backward and lands up in 0, which is less than 5. So N stops here. So you see what has happened now. So now M and N kind of switched position at this point. Okay. So where they switch, so repeat, so we can say now repeat while, or not while, but repeat until M is greater than equal to N. Okay. So you can see at this point, M is actually greater than N. Okay. So it is going to stop. Now, what do we do after stopping? So at this point, we need to now bring back the pivot to the middle again. So now you can swap. So at this point, we can swap the pivot with A of M. So what happens when you swap? So we have 3, 4, 0, 9. So at this point, you have actually swapped these two, right? So let's just reflect that. Okay. So at this point, you have 0 coming here and you have 5 coming here. And you have got 8, 7, and 9 here. Okay. So now 5 returned back to the position. So remember, this is our pivot. So what did we achieve here after doing this? So you can see now, whatever is there on the left-hand side of the pivot that is less than the pivot, and whatever is on the right-hand side of this is now greater than pivot. So that's what we achieved here. And the next, we are going to work on this side and this side by recursively calling. But you get the picture now. Any questions so far? So now we are ready to write down the algorithm. Okay.
Wait, is this like a worst case or a best case? Because like it seems like a lot of steps, even though you said it's like efficient.
Which appear to be a lot of steps here.
Well, like the comparing part, maybe. Yeah.
Yes.
Like
So,
advancing and decrementing M and N.
right. So that's why we laid down in this picture, right? When we were laying down. So it has to perform these many operations in order to figure out whether, I mean, in order to not figure out whether, but in order to reorganize them. So at this step, it has to go through the half of them getting compared with the pivot. And likewise, this other half getting also compared with the pivot to find the right place. So now the thing is that if you try to break it down at every step, like you can see, ultimately it comes down to you have only one element, right? And when you have the one element, then it is just a concatenation. So in other words, that the comparison that you made at each step, it is surely going to be order of n, right? That's why we multiplied the order of n with the log of n. The speed of this is going to come from how effectively you're choosing the pivot in such a way that it reaches the closure faster. Is it making sense?
So you're saying like,
So at every level, we are accounting for the fact that it is order of n, right? At every level. But our goal is like, can we have it as log of n, right? Levels, as opposed to this worst case possibility where it became n levels. So that's one aspect. The other aspect is that how we are actually reorganizing these, it leads to lesser and lesser number of comparisons that are needed at every step. Is that okay?
wait, so you're saying like, so even before we start recursively resorting the array, right? Like once we get to the place where it's like 3, 4, 0, 5, 8, 7, 9, you're saying like, what's the most efficient way to organize it so that half of it's less than the pivot and then half of it's greater than the pivot?
Yeah. It's basically, it's essentially how you are selecting pivot at every step and how you are moving closer and closer to the solution. It's just achieving the closure faster. Now, the proof of how in the average case it is n log n. It is a little harder theoretical sort of proof. It's easy to show that it is n square, right? Because in the worst case, you will have n number of levels, right? And at every step, you can see that you're doing n comparisons, right? And therefore, you will end up in order of n square. But to show how in the best possible case, it actually does faster than other n log n algorithms, that's a little hard to prove. And that is why we are making sort of like a handoffish statement by saying that in practice, this tends to be having much faster complexity or much faster turnaround time. But at least you can intuitively see this point that at every step we are making n comparisons, and if we are able to select pivot in such a way that there are n that there are log n levels, then it is n log n. So it's not like too much operation going on, it's just order of n operation. Is that okay?
Yeah, thank you.
Okay, so now let's write down how the quicksort would look like in action based on the strategy that we just talked about. So we can say qsort, and again we are providing a, I, and j. So first step is if I happens to be greater than equal to j, right? It's exactly the same kind of step as the merge sort you return. Okay. So now the next step is the pivot selection. So let's say p index equal to some strategy. So some strategy in figuring out what should be the index. And we discussed that there are two possible ways you can choose, at least as far as this course is concerned. You can choose the randomized strategy, or you can choose the median of 3 strategy. Either of them is fine. So your pivot after you have selected this, right, index is going to be a of p index. Okay. So after you have determined the pivot, so this is the selection. So this is the step of your pivot selection. So after you have selected the pivot, what is the step that we did for in place is that we swapped pivot and the last element. So you swap pivot and a of j, right? So how do you swap it? So you say a of p index, because you have already selected, right? So it is already saved into pivot. So you can say a of p index is equal to a of j. So you brought into the last entry, you brought into the middle position, wherever that p index was. And then a of j is equal to a of, actually we already saved it, pivot, right? So this is where we swapped. Okay. So now we know that that at this point m sandwiches the array so we want to make m equal to I minus 1, right? So m sandwiches the array from the left, and likewise n, you want it to sandwich the array from the right. So your n is going to be equal to j. And remember, we are doing everything between I and j minus 1. That's our range in which we are applying. So what are we applying here? So we run a do while loop. So at every step, what we are doing is that we are incrementing m forward, right? How long are we incrementing? While we are encountering the a of m entry to be less than pivot. So as long as these are less than pivot, keep incrementing. And likewise, we are decrementing n while we find a of n to be greater than pivot. But that's not all, because if you keep incrementing n, you may hit, you may end up going beyond I, right? So therefore, you need to put one more condition, which is n should be greater than I. So as long as n is greater than I, then you're fine. Okay. So after doing this, then you check. So it's going to exit from here, exit from this do while loop when we find that a of m is greater than equal to the pivot, right? That's where it is going to stop. And likewise, this is going to stop when it is either hitting n equal to I, or it is hitting a of n to be less than equal to pivot, because that's the time we want to swap. So if we find that m is less than n, okay, then what do? You swap a of m and a of n. Is this point clear? Remember, the swapping is being done as long as the m and n have not crisscrossed. I mean, they have not crossed themselves. See, if you remember, like once they have crossed the position, right, we didn't swap. So swapping is going to happen as long as m is less than n. We don't do the swapping if it is crossing each other. Okay, so that's the logic here. So if as long as m is less than n, we want to swap them because it has violated the condition that a of m is less than pivot. And likewise, it may have violated the condition that a of n is greater than pivot. Okay. And we want to do this while m is less than n. Right? Because what's going to happen when m is greater than equal to n? So either it is kind of coincide into one point, or m and n has crossed each other. So at this point, what we find is that m is greater than equal to n, and therefore we know for sure a of m must be greater than the pivot, right? So if a of m is greater than the pivot, so now we can bring m to the bring the pivot to the middle. So at this point, now we can swap the pivot back to the central position. So hence it is now okay to swap the pivot. So pivot is in swap the pivot which is currently in a of j position, right, with a of m. So what can we say? We can do a of j is equal to A of M, right? Pivot we had already saved, so we can use this. So we had already saved here. So we can now bring A of M. So this is in the middle. We bring the pivot back to the position. Okay. So after doing all of this, what is remaining to be done? Just the recursive call. So quick sort A, we are running I to, at this point, M minus 1, right? So remember, at this point, what do we need to do? Here, right? We have achieved, like, all the elements are now less than pivot and all the elements here are greater than pivot. 5 is just staying there. There's nothing else to be done. So we just need to call quicksort on this and call quicksort on this. And that's all is remaining to be done. So it's going to be calling I to M minus 1, because this position is M minus 1 and this position is M plus 1. And this position is I and this position is J, right? So therefore, we are calling quicksort recursively from I to M minus 1 and quicksort A M plus 1 to J. And the concatenation is just happening implicitly. There is nothing else to be done. And we are done with the quicksort. It's a very, very elegant in-place algorithm. So what we have written down here is an elegant in-place Q-sort algorithm. Any question?
Yes, I noticed that you didn't include in the do while, you didn't include the condition when AM equals to pivot or AN equals to pivot. Is it the design to be such way that if there are multiple values that's equal to pivot, they will end up in the middle of the array after this whole thing?
Correct.
Or
correct. It's a good question. Yeah.
And that's the rationale behind it,
yes.
right?
Yes.
Wow.
So you can try something out, and then maybe next week I may touch upon that point. I want you to experience a little bit on your own when you're implementing. That way the point will go deeper. Okay, but thank you for asking the question. So next week when we are meeting, I would like to touch upon what happens when there are repeated entries, you know. But I would like you to try this out, okay, with repeated entries and try to understand on your own. Is that okay? Sorry, I just wanted to double check. Is that okay with you with that?
Yes, thanks.
Okay.
Sorry.
All right. All right, so I'm going to stop.